Okay, good day everyone. It's a wonderful Saturday. Today's program is brought to you by the Warsaw Quantum Computing Group and the other organizers. Today's topic is on optimization of reversible circuits, on Toffoli decompositions and negative controls, which will be given by Marianne Medart. I will be introducing the speaker in a while. Just before we give the podium to the speaker, I would like to give you some background information on our upcoming events. Next Saturday, which is October 9th, we have a topic that would be on quantum interference of light that will be given by Professor Enrique Galvez. And the moderators would be Javier Oduz and then Sebastian Zahak. Please be here and you would definitely enjoy the program. Also, we have another coming up on October 23rd, which is going to be between 1 p.m. and 3 p.m. Eastern time. Please check with your local time to be sure you have the correct timing. This is on the topic of pivoting into quantum computing and solving industry challenges with Cambridge Quantum. And this topic of the program would be given by Danica Annan from Cambridge Quantum. This will be moderated by people like Sebastian, John Barnes, Chris Bishop, and Raphael Sotelo. And so please be sure to join in to enjoy and learn from these programs. Also, we have modeling a theory of gravity using machine learning. The speaker of this topic is going to be Saad Nahim, and the moderators would be Arusa Ayaz, Mena El Marsri, and Powell Gora. This program is scheduled for November 6th between 1 and 3 p.m. Eastern time. And please also check with your time as well. In addition to that, we have why Pauli exclusion principle applies to bosons, a deep dive into the quantum computing and hardware from a chemical physics perspective. This would be given by the speaker, Dr. Kipa Sharkey, and then the moderators would also be Power Gora and Sebastian Zayak. We would like to give you a little bit of introduction to know about our sponsors. On the list, we have Quantum AI Foundation, the Warsaw Quantum Computing Meetup Group. We have the website here, and the organizer is Power Gora. Please be sure to visit the website for adequate information about coming events and the likes. In addition to the sponsors group, we have Alexandria Quantum Computing Meetup. We have the Facebook webpage here. Please be sure to visit these pages to get information, and the event organizer is Karim El-Safti. In addition, we have Quantum Computing and Data Science Toronto, Ontario group in Canada. This event organizers are Enin Dekant and Young Chung. Please be sure to check the website as well to get enough information. And then we also have the Minnesota Quantum Computing Group. The Meetup Group's website is up here as well, and the event organizer is Danica Annan. And then we have OrionX.net as part of the sponsors as well. We have the website up here, and then the founding partner is Shannon Khan. We have also Association Quantum, whose founder is Jeff Lowy. The website is as well on the screen, and please be sure to check this website. Also, we have the Q Mexico, whose coordinator is Dr. Javier Oduz. We have the website up as well. Please be sure to check it for coming events and information. Also, in addition, we have Q Egypt from the Q World group. We have the members being Karim El-Safti, Dr. Ahmed Yuns, and Miriam Gado. Please be sure to check the website and visit for more information. Yeah, we have Q Poland, who's also like a part of the Q World. The members are Paul Gora and Sebastian Zayak. Please be sure to check these websites to get enough information about upcoming programs and learn more about quantum computing and news in the quantum computing field. All right, we will be introducing the speaker of the day, who is Marian Gado. She will be speaking on optimization of reversible circuits. Just before we let Miriam begin our presentation, I would like to let you know that Miriam obtained a bachelor's degree in computer science, a special degree from Alexandria University in Egypt in 2016. And she's a Master's of Science student of computer science as well at Alexandria University in Egypt. Miriam is a member of the Alexandria Quantum Computing Group, and she is currently a teaching assistant. She's a teaching assistant at Egypt, Japan, University of Science and Technology, EJUST, where she was a research assistant and a laboratory engineer from 2017 to 2020. And without further ado, we would like to let Miriam begin her speech. And while the program continues, please feel free to leave questions on the chat group. And once the speaker is through with us, a presentation, we would open up the stage for questions. Thank you.
Thank you so much, Lawal. I will begin my presentation now. Okay, today I'm going to talk about my research field, which is optimization of reversible circuits, and especially about using decompositions of Toffoli with negative controls. So this is the outline. I will firstly talk about reversible circuits, then the quantum cost of reversible circuits, the new negative NCT library, the two algorithms that I have developed, and the experimental results. So in my beginning of the speech, I will talk about the libraries or the generators of classical and quantum computers. Maybe all the people are aware that there are classical universal gate libraries like NAND, NOR, NOT, and OR that are used to build certain circuits. So in reversible logic gate, there are gate libraries like NCT, which is using Toffoli, C0, and NOT gates, and ensure the reversible circuits doesn't lose heat according to the previous research. So let me, okay. So talking about the reversible gate libraries, such as NCT, it consists of 3 types of gates. First one is one qubit gates, 2 qubit gates like C0, and 3 qubit gates like Toffoli. The 3 figures that illustrates the 3 types of gates. The first one in figure A, the N0 gates can be applied on the first qubit or the second qubit or the third qubit. Then the C0 gates, it's applied on 2 qubits. So it has a control and a target. And the Toffoli gates have 2 controls and 1 target. So in order to see the functionality of each gate, like the NOT gate, if I have an input of 0, it negates it. So if I have a wire that's have a value of 0 and then applied the NOT gate, the value is going to be transferred to 1. And vice versa, of course, if I have 1 and then applied NOT gate on it, it's gonna be 0. The second one is the 2 qubit gate C0. It consists of 2 qubits like here. So if I have a state like 0 and 0, it will not be changed because this control is positive control. Positive controls means that this gate is only applied if the control qubit value is 1. So this is the first qubit and this is the second qubit. So if I have 0 and 1, 0 means that the gate is not gonna be applied. So the output is gonna be 0, 1 as it is. Interestingly, if I have 1, 0, that means that the second qubit is gonna be flipped. So the output is 1 and 1, and for the final one, 1 and 1 gives me 1 and 0. The same is applied with latency. The same is applied on the Toffoli gate. Toffoli gate has 2 control qubits and 1 target qubit. According to the which qubits are the control qubits, it gives the output. So here, if I have 0 and 0, it remains the same. You have 0 and 1, it remains the same. It only works if the first 2 qubits are 1s in order to give me a negation on the final output. This is for the Toffoli 123. Of course, there is a different truth table for Toffoli 132 or Toffoli 231. So this is just an example. And then I found that there are 8 different decompositions for the Toffoli gate. What is the meaning of that? The meaning of that I can use, I will go back one slide. I will use this gate. This gate can be replaced with a combination of different elementary gates. So, and they give the same result. These decompositions are used in order to find a possible optimization techniques in order to lower the quantum cost. So for this paper, it's not my work. This paper has the 8 different decompositions for each of the 3 Toffoli gates that work on the 3 qubits. So this is the first one, it's Toffoli 123. This is the second one, Toffoli 132. That means that the control qubits on the first qubit and on the third qubit. And then the target qubit is the second. And finally, Toffoli 321. That means that the control qubits are on the second wire and the third wire. And then the target qubit is the first wire. So let's talk about the quantum cost that I have just mentioned. The quantum cost of a reversible circuit is the number of elementary gates that can be used in order to simulate a certain circuit or a certain permutation. So if I have 2 equivalent circuits that have the same truth table, I can compare between them regarding the number of elementary gates that can be used in order to construct this circuit. So I have 2 metrics in order to measure this quantum circuit. The first one is the cost 015 metric, and the second one is cost 115 metric. So what's the meaning of cost 015 metric? It means that the cost of any 1 qubit gate is 0, like the NOT gate that we have talked about. The quantum cost of 2 qubit gates is 1, like the CNOT gate. And the quantum cost of Toffoli gate is 5, because Toffoli gate can be decomposed into 5 different elementary gates. And there's another metric that's cost 115. Cost 115 measures that 1 qubit gate cost is 1, 2 qubit gates cost is 1, and 3 qubit gates is 5. So optimization of reversible circuits aims to reduce the number of, to reduce the quantum cost of the number of elementary gates of any reversible circuit. So how to achieve the optimization is by applying some moving and merging rules. So I will give you like a brief on what we are doing in this field. Firstly, if I have this N1 gate, what's the meaning of that? The 3 that exist in the like superscript it means that this gate is applied in a 3-qubit system. And the subscript 1, it means that this NOT gate is applied on the first qubit. So if I have this NOT 3-1 gate, it can be swapped with N to a 3-2 gate or N3-3 gate. That means that any of the other NOT gate that are applied on the second or the third qubit. Another thing, I can swap this 1-qubit gate with another 2-qubit gates if the control qubit that's in the 2-qubit gates are not as the same qubit that NOT gate is applied. If they have the same qubit of if they have the same control qubit, I can't swap them. The same idea goes with K1, 2, where K is any 2-qubit gates. The first one indicates the control qubit, and the second one controls means the target qubit. This is for the moving rules, and some merging rules are applied. So if I have the same gate applied on the same wire or the same qubit, they give me identity. If I have like V or V dagger gates, they also give me identity. If I apply and so on for the application. So like if I have OV dagger gate followed by C 1, 2 gate, it gives me V gate. This is the optimization rules. And then the problem that we are facing is that the system of 3 qubits has factorial 2 to the power n. So if I'm talking about only 3 qubits, it's 2 to the factorial 2 to the power 3. It means 8 factorial and 40,320 different circuits that I need to optimize. So we want to know the equivalent circuits for each circuit of those 40,320. So for a simple example, if I imagine a circuit that consists only of 2 Toffoli gates, each of these Toffoli gates have 8 different decompositions. So 8 multiplies by 8, it means 64 circuits. 64 different circuits that may be representing this gate. So in order to like expand this example, 3 Toffoli gates, it means that there are 512 different circuits. So it's too much data because not all the circuits consist of 2 or 3 Toffoli gates. It may have taken up to 7 or 8. So imagine the number of data that you are dealing with. That's why we have thought about 2 methods in order to eliminate this huge number of different probabilities. So the first method of the optimization is using negative NCT library instead of the regular positive, because the system tends to be more stable in the ground state. The second method, optimization, is using basic pairs. So let's begin with the negative NCT library. The negative NCT library consists of 3 different types of gates, like the NCT library. The first one is NOT gate. The second one is OC NOT gate. So I have denoted this new negative gate in order to add an O before the C NOT gate. And the same goes for the Toffoli. I have named it O Toffoli in order to address it specifically. So these are the different combinations that can be applied in a 3-qubit system. So the normal NOT gate, it negates the qubit from 0 to 1, from 1 to 0. The second one is OC NOT gate. OC NOT gate is applied if and only if the control qubit state is negative. So it's unlike the normal CNOT. The normal CNOT gate works only if the control qubit state is 1. But in the OC NOT gate, it works only if the control qubit state is 0. So let's see the truth table. If I have the state 0 and 0, this stands for the first qubit, and this is the second qubit, or in other words, this is the control qubit, and this is the target qubit. So the control qubit state is 0, hence the gate is gonna be applied. So the output is gonna be 0 and 1. Another thing, if I have 0 and 1, and then the gate is also gonna be applied, so it's 0 and 0. The third gate now is the Toffoli gate, and it works the same. If I have a control qubit that's 0 and 0, the gate is gonna be applied, and negation is gonna be applied on the target qubit. So 0 and 0, it's gonna be 0, 0, and 1, and so on. So I have created Toffoli decompositions with negative controls that are based on the Toffoli decompositions of normal Toffoli gate, but these are the open or the negative control. So if I have T13, it has 8 different decompositions. In order to address specifically which decompositions that I'm going to use, I have numbered them from 0 to 7. So this is the decomposition number 0. This is the decomposition number 1. This is the decomposition number 2. And this is the decomposition number 3. And so on for 4, 5, 6, and 7. What's the difference between them? It differs from which is the first control qubit and which is the second control qubit. So if I'm talking about T13, if the first control is considered to be 1, it's gonna give me 4 different combination which is seen in A. If I choose that the second control qubit is the first one, so it gives me B. The same applies for all of the Toffoli gates. This is Toffoli 231, and of course it's numbered from 0, 1, 2, 3, and so on. And this is 1, 3, 2. It has also 8 different decompositions. So this is the negative NCT gate. Let's talk about the basic pairs of gates. In order to prepare a basic pair, we have to address some things. Well, one of which is that each gate has gate decompositions. So if I'm talking about Toffoli 1, 2, 3, it has 0, 1, 2, 3, and so on until 7, 8 different decompositions. T132 also had 8 different decompositions, and Toffoli 231 also has 8 different decompositions. The difference here is that gates like C or OC NOT or NOT gate, they don't have decompositions because they are elementary gates. But in this work, I have given them that they have only one decompositions, and this decomposition is called decomposition number 0. That's for simplification in order to choose the perfect circuit. Also, in order to prepare a basic pair, there's an ordered pair. What's the meaning of ordered pair? Ordered pair is concerned only with the control qubit and the target qubit. It doesn't concern with the functionality of the gate itself. So if I have 5 different, which represents T1, 2, 3, and this is the zeros decomposition. So if I have, this is called 1, this is called 2, 3, 4, and 5, And then I want to know what's the OP of the first gate. This is number one. So the OP is concerned with the control qubit and the target qubit. I see now this is the first qubit, and this is the second qubit that contains the control qubit, and this is the third qubit that contains the target qubit. That's why the OP of I gate is 2 and 3. It's written as an ordered pair. And then if I want to know the fifth gate, what's the OP of it? It's gonna be 1 and 3, because the control qubit is on the first qubit and the target qubit is on the third qubit. So let's keep in mind that there is an ordered pair and how to create it. And then I have developed a concept that's called right and left gate set. So what happens here, this is the same example, is that I'm going to create RG and LG sets. RG means the right gates, means right, and LG sets means the left hand side gates. So in order to create an LG or a right G set, we have to know the OP of the very most gate. So if I'm talking about the LG gate or the LG set, contains the OP of the left-hand side gate. So let's see the left-hand side gate of this decomposition. It's gonna be 2 and 3, because the OP of V23 is 2 and 3. Can I swap this gate with the following gate? No, I can't swap, because the control qubit of this gate is the same as the target qubit of the next gate, so I can't swap them. That's why the LG set of this decomposition is gonna be 2 and 3, as written in here. So let's build the RG set. The RG set is the right-hand side most gate. So in this example, it's gonna be V13. It means that the RG is gonna be 1 and 3. So RG set is updated to 1 and 3. But I can see the previous gate. It can be swapped. They can be swapped with each others. That's why I will also add another ordered pair. It's gonna be 1 and 2, because this C0 gate is applied on the second qubit if the first qubit is negative. So the RG set is 1, 3. This is the first ordered pair, and 1, 2. This is the second ordered pair. So after that, I have constructed a table in order to contain all the different Toffoli decompositions, and I extracted the RG sets and the LG sets in order to be able to build the basic pair. So building a basic pair, we first must know what's a basic pair. A basic pair consists of 2 consequence gates, and then we try to best match the LG set and the RG set of the next gate. So let's take an example. It's L10 and L21. That's mean the first gate is gonna be the gate on the left-hand side. It's L1. L1 means T1, 2, 3. And L2 means 1, 3, 2. And it's decomposition number 1. Let's see why I have chosen the first gate in order to be in the 0th decomposition, and the second one in order to be in the 1th decomposition. So looking at the previous table, this is the L1 and this is the L2. So the theory says, or the practical says, that the RG set of the first gate, this is the RG set, it contains 4 different sets, and the LG set of the next gate, and this is the LG set of the next gate. Then I will compare these 2 sets in order to find a match between sets, find the best match. So I found that 1 and 2 the set 1 and 2 that contains 1 and 2 ordered pair with 1 and 3 ordered pair can also be found here. So this is the red rectangle. They are the same. So we have a match. So in order to find a specific example, that's why I have chosen this in the zeros decomposition and this in the ones decomposition. Okay, I will imagine that someone asks me, why did I choose this one? And then I didn't choose 1 and 2 only, because the probability of merging gates is increased if the number of the OP set increased. So this is the 2 is better than 1. That's why I have chosen the zeros decomposition for the first gate and the ones decomposition for the next gate. So let's take the same example and then illustrate it in a visual way. So after applying this algorithm, I have found this is the L1 in its zeros decomposition, and this is L2 in its 1 decomposition. So these gates that are in the middle, they can be swapped in order to, like in figure A, the very most right-hand side gate of the first decomposition and the very most left-hand side gate of the second decomposition can be swapped. So I will swap them. And then figure B is the gates after swapping. First one, I can prepare those rectangles in order to make them create another gate. So if I have a C0 gate followed by a V gate, it can be replaced with V dagger gate, and these can be replaced with V dagger gates only also. So the final result, the next result in figure C, it's gonna be V dagger followed by V dagger. So I will mark the first newly decomposed gate, and then I will move it to the right-hand side. Move this to the right-hand side, means it will be right here. So in D, this gate is gonna be on the rightmost hand side. And then this is the second gate that's formed. I'm gonna move it to the left-hand side. And then in figure E, it's the final result after applying the basic pair method. So it's gonna be create in the middle a newly gate that's has a quantum cost of 1 instead of 2, according to some papers. So the final quantum cost is 7 instead of 10. So I have reduced the quantum costs of these basic pair from 10 to 7. The next one is building a basic pair in quantum circuits. So this is the first algorithm. The first algorithm uses function 1. Function 1 means that the gates are, the circuit is split into basic pairs from the very most left-hand side gate. And then if there a one qubit, a one gate on the right-hand side, it's gonna be a solitary gate. Okay, so let's see an example. If I have this this circuit, it consists of 5 different circuits. So I'm gonna split the first 2 into a basic pair, the second 2 into a basic pair, and the third gate is gonna be as it is. So I will see what is the basic pair of these 2 gates, and then put the first basic pair, see which is the basic pair of these 2, and I will admit it here. And the final solitary gate is gonna be put there. And then in the point of connection, that means that the left-hand side gate of the second pair with the right-hand side of the next pair if they can be moved, or any optimization techniques can be applied in order to reduce the quantum cost. After applying optimization on these point of connections, the quantum cost is reduced from 17 to 11 in this example. And then I have applied another algorithm that's called the modified circuit optimization algorithm. Circuit optimization algorithm uses function 2. Function 2 splits the circuit into basic pair starting from the second gate on the left-hand side instead of the first gate on the left-hand side as in function 1. So let's see an example. This is an example of 5 different circuits. It can be split into these 2 are the first basic pair, these 2 are the second basic pair, and this is a solitary gate. This is if I used function 1. So if I used function 1, the quantum cost is gonna be 10 instead of 11. So let's use function 2. Function 2 splits the basic pair starting from the second gate on the left. So this is the first gate, is gonna be a solitary gate, and then these are a basic pair, and finally these are the basic pair. So after applying this method, functions to quantum cost is 8. So comparing figure B and C, quantum cost of 8 is better than quantum cost of 10. That's why I will apply optimization using function 2 instead of function 1. After applying optimization rules, the final quantum cost is 7. So I have reduced the quantum cost from 11 to 7 using function 2. But it's not always that function 2 is better than function 1. That's why the modified algorithm, let me go up 2 slides. That's why the modified circuit optimization algorithm chooses between the quantum, which of the functions 1 and 2, which one does contain the less quantum cost. So this is what the modified quantum circuit circuit optimization algorithm does. And then I have applied or mapped the negative NCT library on IBM quantum experience from their drag and drop. So the first thing that I faced that they don't currently have a negative control. So I have an equivalent circuit, put a NOT gate before and after normal one. And then they also don't have the dagger. So I decomposed it into another circuit that's are equivalent. And this slide gives me a brief introduction about the two different truth tables. So this is the first circuit, and this is the equivalent circuit if I use negative controls. So this quantum cost is 15, and the quantum cost of the negative NCT library before any optimization is of 8, and then after optimization it's gonna be 6. So I'm comparing 15 with 8. This is for one example. And for the results, after using the algorithm 1 and algorithm 2, the quantum cost is reduced comparing with the NCT library. So comparing NCT library with negative NCT library. The NCT library's best quantum cost was 10.348. It's shown in red. And then if I'm comparing it with the NT library is this blue. And then the purple one means the algorithm 2, and the green one, it means the algorithm 1. So these are the quantum cost compared with the number of gates, and they formally consists of 40,320. So after applying algorithm 1, that means it uses function 1 only, then the quantum cost is reduced to 10.202 compared with 10.348 in the previous work. And then after applying algorithm 2 that chooses between the function 1 and function 2, the quantum cost is reduced to 10.078. Also, the results in the 115 metric, I have compared it with the NCT library, and these are the results. If anyone wants the link of my paper, it can be found on Symmetry Journal. Thank you. Does anyone have a question?
Thank you, Miriam, for the wonderful talk. So we are open to questions. Some questions have been put on the chat, which I will be reading out to you for answers. And if you have questions, please feel free to raise your hand, and then we can give you the opportunity to ask questions.
Okay. I will. Will you read the question for me, or I should read it?
I will be reading them out to you.
Okay.
Yes. I'm trying to see if there's anyone who has questions for reading out.
Yeah, there is a question.
Okay, go ahead.
Can this be formulated as combinatorics problem? Like leaving the hardware considerations, which you are expert in for sure, but translate it mathematically to combinatorics problem. Because you've been using some shift by moving the gates, and also the possibilities and handling it with more qubits beyond the Toffoli, like 5 qubits, 10 qubits, it will be difficult to grasp what's going on. So if we talk optimization, you also mentioned that you want to reduce the cost, but that's your optimization, but you're not minimizing the cost. Are you?
I'm minimizing the cost, the quantum cost.
Or you are minimizing it?
Because
okay, fine. So
in the beginning, I used the Schreier-Sims algorithm in order to generate the set of 4,320 different circuits with the shortest length and the least quantum cost. And then I apply optimization on these. Also for the Toffoli or systems that use like 5 qubits and etc. Each of these like 5 control qubits Toffoli gate can be decomposed into eventually 3 normal Toffoli gates, so it can be applied.
Okay,
thank you for your question.
That's great. So what about my first question?
Which one?
I ask you if there are more qubits.
Yes.
Beyond the 3, then it's a combinatorics problem.
If there are more qubits, it's gonna be decomposed into like eventually 1 and 2 qubit gates in its final form.
You mean any number of qubits you can reduce to 1 or 2?
Yes.
Oh, that's lovely. So can you put or anybody can put the paper on the chat, please?
Okay.
Because you just showed it for 1 second.
Okay. The article will be put on the chat group. The link to get in the article will be put in the chat group. Yeah. So
I think I think there would be just one thing I'd like to say is that I think the questioner is slightly, which I understand his question, he's also asking if there is a circuit reduction, which is essentially optimization. And, you know, although you have a quantum optimization, you may not have the circuit reduction because you're still using the same number of qubits. Is that a fair question to the speaker before?
Yeah, it is a fair question because
at the end of the day, it's about cost.
Actually, this is not the question. And I guess that I have fully answered your question. Thank you so much. I will read now the other questions. Are not C not Toffoli are interchangeable each other. Every gate can be made from these three gates. Not that every gate is gonna be made from these three gates, but I believe that if you have followed my presentation, Mr. Bilal, is your question is your question valid now, or did you understand from my presentation what did you want to ask? Mr. Bilal, are you still here? Okay.
Yeah, so there's another question about what is decomposition of gates?
Yeah, the decomposition of gates, it's like building the equivalent gates from an elementary gate, and they have the same functionality.
Okay, so I think one of the questions that might help in clarifying some things are maybe the term optimization, the way it's being used in the quantum computing world might be quite maybe something we might need to look into, because when you're talking of optimization, you're either minimizing or maximizing something, right?
Yes, minimizing, of course.
Yeah, so in this case,
it's minimizing the quantum cost or minimizing the number of the elementary gates.
Okay, yeah, so can you like give like a general perspective as to what quantum cost is?
What a quantum cost is?
Yes.
According to the cost 015 metric and cost 115 metric, the number of elementary gates, and the elementary gates is the number of what's an elementary gate? It's either 1 qubit gates or 2 qubit gates.
Okay, yeah, so what is the essential difference between the costs 015 and 115?
The essential difference is that in 015, the quantum cost of 1 qubit gate is considered as 0, and the quantum cost of 1 qubit gate in cost 115 is considered to be 1.
Yes, and for one, okay, so what does that really mean? What does that imply?
I don't understand the question.
Yeah, when you said the cost of 1 qubit is 0 for the cost 015, right? And then for that of 115, because they still have the same amount of the 2 qubits, which is 1, and for the 3 qubits, which is like 5 for the Toffoli, right? Yeah. They have same numbers for those. So for the cost 015 and 115 that has 0 and 1 for the 1 qubit, what does that really, which is like the essential difference, what does that really mean?
That means the quantum cost is either 0, 1, or 5. I really don't understand what's not.
So in terms of application, when we talk about the cost minimization, what does that, for the cost 015?
It means that I can apply the certain circuit with a less number of resources.
Oh, okay. All right. So another question here says, how can one do a read or write with a reversible gate?
Read or write?
Yes, with a reversible gate.
No, can you please tell me the question?
Okay, yeah, so it says, how can one do a read or write with a reversible gate?
read or write in a reversible gate. I don't think that this is the scope I have talked about in particular. But if you are talking about the permutation of each of these 40,320, so it's like permutation. I will show like a part of my paper. Let me show it to you now.
Okay, that's fine. All right. So while you're doing that, another question from the audience is that is there a situation or where ancillary qubits are used?
In my work, no, I don't use any ancillary qubits. That's why it's using the minimum number of qubits. No ancillary qubits are used in my model.
Okay.
So I will share it now. So these are the permutation that's for each of these 40,320 circuits. And it's represented as disjoint cycles can be written as this. So I like simulated each of these in order to know which of these are exactly gonna be used in order to build specific circuits for the 3-bit quantum circuit.
Okay, great. Thank you for that. So there's this question from the audience as well that you essentially have answered the first part of it, where you talked, the person asked about defining the meaning of quantum cost. And a follow-up to that is that what do you see as the essential trade-offs?
Essential what?
Trade-offs.
Can you please define what you mean by quantum cost and what do you see as the essential trade-off?
Yes.
I believe that I have answered this question. Could you please speak a little on V gates? V gate is the square root of NOT gates, and they have two versions, V gate and V dagger gate. Why does IBM not directly provide in this quantum assembly language? I don't know. I don't know why IBM is using V gate but not using V dagger gate. I hope that they will develop, they will expand the system in order to accommodate the V dagger, also the open controls. I guess that they will do that in the future, but I'm not sure.
Okay, Miriam, so a question is about, like, does the order of qubits determine which is control or target?
The order?
Yes, the order at which the qubit are being written. So take, for example, a 3 qubits that says, you know, the ket of 000 or 001. Does that order determine which one is control qubit?
Yes, sure.
Or target qubit?
Yeah, sure. If I am talking about like 000, it's read from the left-hand side to the right-hand side.
Okay. Yeah. So, what is the effect of the V gate when it's applied to a qubit or 2 qubits?
So the effect is like a number of imaginary parts, of course. So I have replaced it with like positive or negative in order to like make things simpler. So this is a gate that can be applied and people can search it. It's the square root of NOT gate.
Yeah, okay. So it's more like, so the question is more of, you know, when we have the NOT gates, which, you know, changes the state of qubit from 1 to 0 and 0 to 1.
Yeah.
What's like the operation of the V gate? What does it do to qubits?
The application, yes.
Yeah.
If the V gate is with a control, of course, either the control qubit is negative or positive, that means that it's gonna be applied or not. And then it converts the state from like plus to negative. I will also share with you. this part. Yes, this is okay. So there is positive and negative. Positive is this state, and negative is this state.
Okay.
Sure, have an imaginary part. And then for simplification, if I have a V gate that's applied on a qubit, it maps 0 to positive and 1 to negative, and it maps positive to 1 and negative to 0. The same goes for V dagger. It maps 0 to negative, 1 to positive, and positive to 0, negative to 1. Okay.
Yes, great. Thank you for that. Do we have more questions from the audience? Okay, I do not see any question right now, but I have a personal question. I was reading your article, and there's a part of it that identified that there are like 3 optimization rules: moving, merging, which you talked about, and then splitting. And then it talked about that the splitting rule is the reverse of the merging rule. So
yes.
How does that really work?
The splitting rules or all of these?
The splitting rules.
The splitting rules is the reverse of the merging rules. So okay. I also use the splitting rules when I applied my algorithm on the IBM quantum experience. Like I will share it with you now.
Okay.
Which of these I have used splitting rules? It was this one. Because this gate, in B is the circuit after applying optimization, and then I couldn't apply it directly to the IBM quantum experience because they firstly don't have a V dagger gate. This is the first thing, and the second thing that they don't have an open controls. So the first thing is that I have created all of these open, all of these negative to have a NOT gate before and after. Secondly, I have splitted the V dagger gate into C NOT with V gate.
Okay. So is it safe to say that the splitting rule is like an alternative to the moving rule?
The
merging rule, sorry.
Merging, yes.
Yes.
It's the reverse of it.
Yeah. So is it like one can use either of the two?
Yes, it can be used, of course. But in order to minimize the number of qubit gates, it's better to use, it's not better to use the merging rules, but it's logical that you need to minimize the number of quantum circuits, not expanding it. So that's why you mainly use the merging rules, but you have to use splitting rules in situations like this because you don't have another option.
Right. Okay, thank you for that. So a question from the audience says, the person is wondering if there is a cubed root of NOT gate. Do you know if there's anything like that?
Q groups, I am not, I didn't hear this a question before, sorry.
Oh, okay, yeah, so the person is wondering if there is a cubed root of NOT gate.
No, I didn't hear of a cubed root like of NOT gate. Maybe there will scientists will invent something like that, but until now I didn't hear this suggestion in any papers that I have read or something like that.
Okay, awesome. Yeah, so another question from your article, when you were talking about gate symbols, so where you add the L with the underscore of NOT, are these gate symbols unique to particular gates, or they can just be defined?
No, it's not a particular gate. It's like I have given it a symbol, like 0 stands for T, like L1 stands for T123, L2 stands for T132, and L3 stands for 231. It's
Okay.
not something standard, but in the paper, it's really illustrated well that you will go with the flow of the paper and you will understand everything.
Okay, awesome. Thank you for that. So do we have further questions from the audience?
Yeah, can you put it on the chat? The link to the paper?
Yeah, sure. I will put the link of the paper.
Thank you.
You're welcome.
And Marianne, I know you've answered this question before. So
Okay.
how does the optimization of quantum circuits help in creating or constructing quantum computers?
Now, could you please paraphrase this question again?
Okay, so when we're talking of optimizing the quantum circuits, right? How does this influence the creation of or construction of quantum computers?
Yes, they affect this.
In what way, if you may?
I actually not aware of it because my work is not in the physical quantum computers or quantum hardware.
Okay, awesome. Thank you. So just a general note, because we have people coming from different backgrounds and diverse regions. So how would you describe quantum cost to someone who is actually new to the field of quantum computing?
New the quantum computer, I will say that the quantum cost is like I study which are of these quantum circuits or quantum gates, which of these gates is the elementary gates. Elementary gates is the number of, or not a number, the elementary gate is the 1 qubit gate or 2 qubit gates only. So if it's 1 qubit gate, the gate is applied on the qubit that exists on it. And for the 2 qubit gates, it has a control qubit and the target qubit. If I have a circuit that consists of these, I can like count the number of gates in a certain circuit. So let me share with you the presentation again.
Okay.
Or like part of the paper. So it's like if I am counting the number of circuits.
Okay.
So for this circuit, it's L1 0 decomposition. I can count. This is 1, 2, 3, 4, and 5. So that's why the Toffoli gate has quantum cost of 5. If I have another example, let me see another example. This one. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's why this basic pair quantum cost was 10. After applying the optimization, I can count them. This is 1, 2, 3, and this is considered as one gate. So this is 4, 5, 6, and 7. It's really normal counting like we have used to count while we were young, but of course it needs an automatic algorithm in order to calculate all of the 40,320 different circuits.
Oh, great. Thank you so much for that. So one follow-up question that I have is that I was reading an article on quantum machine learning, a review article by Peter Wittek, Jacob Monte, and I believe Seth Lloyd. And they in the conclusion, they talked about 4 problems that quantum machine learning is actually facing at the moment. One of which is the input problem, output problem. And then there's this particular one they talked about. The third one, it says the costing problem. So I'm trying to, and then when they try to like explain what the costing problem is, they were talking about knowing the amount of gates required in a quantum machine learning algorithm. So is your work somewhat related to solving the costing problem of quantum machine learning?
Actually, I have read papers in quantum machine learning, but it's not my area. It's not my specialization, but I have found they use different types of quantum cost functions.
Okay.
But it's like more used in quantum machine learning. But when I searched for what metrics were used in quantum optimization of circuit, it's the most popular tool that you can compare your work with is the cost 015 metric and cost 115 metric. But of course, there are other metrics, especially used in quantum machine learning.
Oh, okay. So is there any particular reason why we tend to use the cost 015 and 115?
Could you please try this again?
Yeah. So is there so it looks like the cost 015 and 115 are the most popular. Are there any particular reasons attached to why we use these two metrics?
Yes, actually they are the most popular ones, and I have used them because eventually I need to compare my work with previous work. So in the previous work in my field, which is optimization of reversible circuits, it's either use cost 0115 or cost 115. That's why I have used these two metrics.
Oh, awesome. Thank you so much.
You're most welcome.
All right, I'm checking through to see if there are...
Yes, there is one.
Yes, please, go ahead.
And this is, since you are optimizing within the gate, can I ask you, can this be generalized to optimize the number of circuits?
To optimize the number of circuits?
Yeah, maybe it's a very ignorant question. I don't understand the hardware too well, but if we want to what is optimization or cost optimization? We want to simplify stuff, right?
Yes, not just simplify. It's like reducing the quantum cost. Reducing the quantum cost means
yes,
that
you are very clear about that. Very clear about that.
Yeah.
But the more circuits I have, the more complicated it is to even understand the system. And maybe your way will be useful to reduce the number of circuits.
It's not the number of circuits, it's reduce the number of gates inside the circuit. Because if I'm talking about the different combination for 3-bit circuits, they are like fixed. They should be like factorial 8, which means that 40,320. I can't neglect any of these combinations except for the identity gates, of course. That means that the 40,319 circuit, I can't like ignore any of them.
You mean each one of them having essential task?
Yes, each one of them has essential tasks, and all of them are different. There is no replication in them.
Okay.
Thank you for your question.
Well,
I have read that. Could you please try again?
I was just curious. It's not.
It's okay. It's okay.
Question. It's being ignorant. You know, this field is so
no.
challenging.
It's like you're trying to to know, and this is good. I like people who are trying to for Abhanendon and F. No, you can search them. You can search them, of course, and you can find the answers. It's not like the normal NOT gate. If you are talking about the normal NOT gate, it's really different from applying V or V dagger gate, and you can search about them in many papers that have talking about these states. Thank you.
Okay.
Is there any other questions?
Yes. So there is this question from one of the audience. It says, what is the definition of reversible gates? And then the follow-up question is, are non-reversible gates possible in quantum computing?
So if I'm talking about reversible gates, it's if I'm talking about the normal classical gate, the normal classical gate like an AND gate. So an AND gate only works if the two inputs are two wires and one, and then it gives only one answer, it's gonna be one. So if I have 0 and 1 or 1 and 0, and the answer is gonna be 0. So in the end, if I have 1, I definitely know the first inputs were 1 and 1. But if I have a 0, it's either can be 0 and 0, 0 and 1, 1 and 0. And this means that I can't know the output from the input. This is a classical, I can't know the input from the output. And this is a classical gates. But for the quantum gates, I can know the input, what were the inputs if I have the output. That's why there's no data is destroyed. Everything is in there. So if I have a circuit that consists of 3 qubits, I must maintain that these 3 qubits is gonna exist in the final state. So that's why I can see which gates are applied or something like that. So the reversibility of the gates, of course, is like decreasing the heat dissipation, like Bennett have published in the 60s, and systems like that are closed. So there is no information is destroyed from them.
Okay, thank you for that clear explanation. Also, the follow-up question is, are non-reversible gates possible in quantum computing? Do we have gates that are non-reversible?
Gates are not, I didn't try to simulate that.
Okay.
But I believe that with reversible gates, you can make like an AND gate or NAND gate. There are people who have applied the full adder or the half adder, but this is not my work, so I can't talk about. Unfortunately, it's not my area of specification.
In reality, though, is every gate is non-reversible because of the loss of energy. But this is a semantic consideration, the codifying of this theory that we're building towards quantum computing, that technically they're reversible, all the quantum, but in reality they're all non-reversible. So I mean, essentially, if I could just give you an example, I mean, if you play a snooker, you're playing a and you hit the snooker ball, yeah, there is no chance in real life that the snooker ball reverses back.
Talking about, but in this context, we say that they are reversible or irreversible according to the number of input and the number of output that we have obtained. I know in practical ways, of course, there are some error threshold, but this is not in science. In science, we call some gates that are classical gates and they are irreversible, and the quantum gates or reversible that are based on reversible computing that are reversible. We don't say that, we don't call a Toffoli gate that it's irreversible. It's reversible. So thank you for your comment. All quantum logic gates are reversible. Yes, I believe so that all quantum logic gates are reversible. Okay, so quantum reversible gates avoid the Landau limit. I am not sure of what is this question about. I believe other gate is reversible using an ancillary line. Again, I didn't use any ancillaries qubit in my work. Thank you. No, thank you.
I have a question. Will you try 4-qubit circuit in the future?
Yes, I would like to try this for circuits or in qubit circuits in order to see if I can like reduce the quantum costs more. Reduce the quantum cost more.
Thank you.
You're welcome.
So Miriam, your work, would you classify it experimental or computational?
It's not experimental, it's computational. It's theoretical. I didn't apply. I applied it on the quantum simulator, not simulator, the quantum computer that IBM have applied, but it's not that I have built a circuit from scratch like a material or hardware. But its concept can be applied, of course.
Okay.
As far as I know, there is no hardware that currently exists for the actual implementation of circuits.
Zoom caller, thank you so much for your questions and your comments. I guess that you are talking about the science itself. You're not my work. I would really
no, I'm asking a question.
If you have a question regarding not knowing the method that I have used exactly, this is the kind of questions that I would like to hear. But questions like questioning the science itself, I can't really answer them all because I just have my master's degree and will start as a PhD degree. I didn't create these sciences, and I see that your most comments were about the science itself. It's like theoretical way how that you want to call the reversible circuits to be irreversible or something like that. It's really like you think, and this is really good, but I don't think that your questions it can be in this place because I don't know. You can like ask me about you can ask me about my work itself. I will gladly answer it, but things other than that I can't really like answer your questions. Thank you so much, and I guess that you are really a thoughtful person, and I like that you have those kind of questions, of course. Thank you.
No, my question to you is, sorry for that, and the question is that, do you know of any, as far as I know, there is no implementation of quantum circuits currently in physical layer. Do you know of any, or if there's any, I mean, have you seen anything in your work so far?
I believe that the IBM quantum experience is not only simulations. I believe that they have a real quantum computers.
Oh, yes, they do, but I mean like the physical circuit implementation.
No, I didn't apply the physical circuit implementation, and I would like to, if you know a place that can be like share my work with them so that we can implement the real circuit, I will be gladly happy to join this project. Thank you so much, Mr. Zoom caller. And thank you so much, Mr. George.
Anybody can put the paper on the chat, the link.
Yeah, yes, I will. This is the link for the paper.
Oh, cool. Very polite and very nice. Thank you.
Thank you. Thank you so much.
You're very kind.
Thank you.
Oops. Why it doesn't go? No.
So is there any other questions?
Yeah, it's continuing your question, which I started it actually, with more qubits. What's the future directions? Of course, you don't have to tell us about your PhD, it's too early. But if you can talk about future directions of these, that will be very nice, but understandable if you decline.
It's like I will try to figure out new methods in order to reduce the quantum cost, and I would really like to extend my work from like 3 bits only to like n bits, like 4, 5, and 6. This is mainly what I aim to do.
Great. And good luck.
Thank you. Thank you so much.
You're welcome.
So if there's no more question, we can close. Thank you for the presentation, Miriam.
Thank you so much, Helen.
Thank you, Helen.
Thank you everyone for joining in.
Great talk. Very
Oh,
nice talk.
I was hoping, you know, I mean, if you wanted to discuss a few things, you know, while, you know, waiting for once the speaker is finished, we could, you know, look at the overall, the bigger picture of it, but if everybody's leaving, that's fine.
Yeah, that will be good.
Helen, is that okay?
Oh, sure, yes.
I think one of the things I wanted to say earlier, and is mostly with regards to that, you know, the gates we're talking about and the circuits we're talking about. If you look at the classical side, you've got your actual circuit that's actually printed on a circuit board. Yeah, so when we talk about circuit, it's actually a circuit that gets printed on. But in quantum, it's purely a logical codification. It is not an actual circuit. We call it circuit, but it is a logical circuit. So you could actually have a half adder, a full adder, or a NOT gate on an actual chip in a classical computing. Whereas in your quantum computer, currently, I do not know of any existing one. And I could be wrong, which is why I asked the question earlier. And if anybody knows one, I would be very happy to hear of one. Yeah, that's part one. And the other part is in terms of this optimization that we're looking at, which is what this whole topic is about. We only looked at one side, which is a circuit-based optimization. But this is back to the old days when computing was developing in the classical world. this is the dilemma of particle versus wave. And what is quantum? Quantum is actually a wave. But when you talk about circuits, you're talking about discretization of the circuit itself. So that's when you talk about 0 and 1, but essentially it's a wave. And in reality, what does optimization really means is this Hamiltonian, this lowering of energy threshold. And in the computer world, we've got two different type of computers. We've got your gate-based quantum computers that are developing. We also got adiabatic quantum computers, which is your D-waves and the waveform computers. So when we're talking about efficiency, the whole idea is that we are actually trying to reduce the energy. And when we talk about reversible circuits, what we're essentially talking about it, can you reverse back to your original state? And I think to understand this whole really, then only you can add the mathematical, because you can do all that mathematics, which we're looking at, but it's only when you understand this physically, what it really means, can you actually, then you can look at optimizations of different types. And essentially it's all about because anytime you do reversibility in real life, you have an entropy. What does that mean? What that means is that if you drop a cup from the top of your hand, the cup will never go back and reassemble it from a broken cup into a real cup. A cup once broken will remain broken. You will never find in nature anything that reverses itself. But in quantum computer, we talk about reversibility, which is your reversibility of circuits, which means if you provide two inputs and an output that's coming out, it can be reversed back into. That's exactly what it means by reversibility. And I just wanted to draw that distinction to understand, so that people, follow what it really means, if you know what I mean. Because then we can have a more thorough discussion for everybody else. And I'd like to hear other people's view.
Yeah, questions to you. That's very nice and very exciting. But do you mean in terms of the universe is always expanding, so the entropy is always increasing?
Correct,
right?
Correct.
So the universe, once it's exploding, it can go back to the 1 minute before the Big Bang, which is then reversibility on the huge, largest scale that you can imagine.
Correct.
So that means now that when, and hopefully not in our times, I'm laughing, it will never explode in our times.
Well, I'd like to add two different things there. I'd like to just to interrupt you there, two different things. Firstly, there's a recent research paper that I read, and I don't have it to hand. Sorry, I can't give it to you, but I think if you Google it, but just to say on that bit, quantum properties so far were believed to be at the quantum level. So things that are happening at the quantum level, which is, at the level of photons. And I don't like to use the word electron because obviously they get, jumbled wide magnetic fields and all manner of things. But at that quantum level, which I suppose everybody understand what I'm talking about, quantum phenomena is real. It's not some made up thing, it's real, right? And, so far the theory has been that what you just described, that Big Bang can never reverse back. However, there's a new research paper published from an Austrian university, which actually challenges this very notion. And what they're saying is that, yes, the effects happen at macroscopic level too. However, we do not account for every other disturbance that's taking place. And therefore, that other butterfly effect that's taking place actually corrupts the whole thing back. And therefore, we'll never reach back. So please carry on.
You have the title of that paper?
I think you might have to Google something like, reversibility, macroscopic quantum phenomena, or something like that.
So microscopic.
Macroscopic, not microscopic, macroscopic.
Macroscopic.
Yeah. So at a real world level.
Quantum phenomena.
Yeah, something like that. You will find few papers.
So what did you say about the perturbation?
Sorry, beg your pardon?
You, in your last or two sentences, you used some perturbation that we don't see.
Yeah, so like basically there are a lot of other entropy effects that are going on, because essentially energy, as we know, always moves from a high point to a lower point. That's a Hamiltonian, right?
Yes.
You go, and you never see energy moving from negative point to a high point. But then the conversion of energy always takes place. So when you say that Big Bang, when it exploded, can we go back to that point? The point is no, because we are not looking at one event in its isolation. There are so many other events that actually are changing that entropy of the system that it will never go back. However, this paper argues if you were to observe one particular event in its isolation, even at macroscopic level, the event can go back.
And that's the beauty of physics, that you can isolate things.
Again, that's theoretically really, because you cannot really isolate anything in physics. Again, these are all, mathematical models. Similarly, the quantum circuit we discussed today is a mathematical model. Reality is, and once we run our algorithm on a IBM or somewhere, what we are eventually getting is the output of that. We cannot actually peek into how it's actually performing, because the moment we observe that, we break out of the quantum system. It's no longer quantum. You see what I'm saying?
Yeah, that's, but in the same time, in physics, you do isolate things, and the only thing you believe in, which I agree with you, mathematics is another thing, but the only thing that we believe in is what we measure, what we experiment and measure. And that's what you call reality, right? So the tool of physics, these two tools of physics, one is you can isolate the system, you can discuss the electron in isolation and write a lot of understanding, namely models, to explain it. This is the beauty of physics. This is the power of physics. And yet, you only believe in things that you can experiment and measure. Okay, but the magic of the good experimenters, their power is that they are able to eliminate all the disturbances to what they want to measure and what they want to focus on.
So with regards to the disturbances part, I'd like to point out one other thing, which the moderator mentioned as well, when he mentioned about quantum machine learning. So quantum machine learning is an area, active field of research in terms of stabilizing the qubit output and input, in terms of reducing that noise. And, I know that there was a discussion in our conversation earlier about the quantum machine learning. So this is one area where this is being actively looked at, how to stabilize a qubit, for example, to have reliability.
Sure. Yeah, but it's not only in quantum machine learning, it's in quantum computer. If the wave function collapses because of the noise or because of the measurement, because you have to do Hadamard, and you have to do, after that, you have to do measurement. Okay? And during the measurement, the wave function may collapse and the whole thing will be an obstruction to quantum computing or building a quantum computer. So it's not a matter of quantum machine learning. Quantum machine learning, of course, noise disturbs everybody. In the same time, there is another notion of another way to look at noise as helping you to find the signal. It's counterintuitive, yet it's a very strong observation.
And there is one paper that I'd like to mention for everybody, and that is to do with not only understanding the basics of this, but the other side of this, because we have a lot of research on the quantum gates side of things, quantum circuits and stuff. And like I was saying initially in my conversation, that's the discrete part of the problem. But if you look at the continuous variable, which is your waveform, you have adiabatic computers. And how do these two actually match up? There's a paper called Gates for Adiabatic Quantum Computing, written by Richard H. Warren. I think it's a very nice, very simple paper. I'd like people to check it out. And that might clear some of these things, with regards to understanding these gates, because he describes these gates very well. And I read this paper, I thought this is quite good.
Cool. Richard, what?
Gates for adiabatic quantum computing. I'll just put this on. But, I think most of the people in quantum world right now, they're looking at the mathematical model. People are designing compilers, people are designing things like that. And those are essentially very different to the wave function paradox. I think my view is eventually the two sides will merge, just like you had, initially they were the people who were into the wave nature of the particle and other people were on the particle nature of the wave. They were both merged by the Einstein's theory of general relativity, that a wave is both a particle and a wave, or a particle is both a wave and a particle. So I think that's what will happen to quantum computing as well. Let me write this down on the chat. The paper, if you Google it, is called Gates for Adiabatic, because adiabatic computing doesn't rely on gates. It's an alternative to, yeah, I think somebody has already put that. Maybe that's the one. Let me just click on this. Yes, I think this is the one. Yes. It's very basic, but it's a good paper to get the hang of basic stuff for a lot of people like myself,
Yeah, thank you very much for this. That's very good.
George, I don't know. I mean, I can come back to you on that. I don't know, but it's, I've saved this paper somewhere. I just need to look at it. I'll go lots of things reading at the same time. Sorry for that.
I think George has a question. Can you reverse wave collapse? Which split did the photon go through?
I believe the answer is no.
All right, sorry.
I don't think I understand the question.
Well, if you measure and during the measurement, you interrupt the system to the point that the wave function collapsing, that's it. You cannot, you stop the process because you have to start it from scratch again.
Agreed.
Yeah, thank you. That was a rhetorical question.
I like rhetorical questions.
And
tell us that it is rhetorical.
Yes, because I believe, and this is stuff that I don't understand about quantum erasing experiments and so forth. But to the limit of my understanding, when you do a measurement, that is irreversible. In a mathematical sense, you're projecting down from a higher dimensional space to a lower dimensional space. So you, at that point, you can't tell which state in the higher dimension gave you that projected state down, unless you've constructed things very carefully so that you can deduce within your basis, maybe. But I don't completely understand that.
Okay, this is beautiful mathematical description.
Yeah.
However, what I'm talking about is about physics, reality.
Yes,
Once
thank you.
the wave function is destroyed, quantum mechanics doesn't allow you to go back.
Yes, thank you. What I meant
You're welcome.
was that,
George, there's one thing that I'd like to add, though, is that, which is there's another caller on the on this chat, Abhinandan. I was having a conversation with him, and last week he asked a question about this, which is slightly related to this, and I'd like to bring it up right now, about the no cloning theorem, right? So which means the information cannot be cloned. And then your question about, hey, you can't really go back. Physics does not allow it. It needs to be in its right state in order to do that. And that's pretty fundamental. Everybody gets that. But I think there is a way which is now used by some of the experiments they're running. If you have a quantum computer and you got multiple copies of that quantum computer, and if you take this quantum computer through a series of steps, and all of them through the same series of steps, that means if they're identical to start with, they all have identical states, correct? And therefore, at some point in time, if you were to expose one of the quantum computer or collapse its wave function, the other are still in its in their primitive state, i.e. their real state. However, as long as they're not quantumly entangled. And therefore, there is I think in Penny Lane, which is the quantum AI system, they use some of these mathematical notions to actually describe this, what does it relate back to? So for example, if you've got a quantum computer A, B, and C, and let's say you observed A, quantum wave collapses, you got B and C, which are identical states, but not quantumly entangled, because if they are quantumly entangled, they both will be affected too. Then you have a way to peek into, or whether you can't really peek into, you have a way to know the original state of A in terms of B and C. You see what I'm saying?
yes, thank you. And again, I don't understand this stuff, but someone has also said that if you claim to understand it, you don't. But if I understand simplifying it, and I'm also more of a mathematician than a physicist, that if you do a measurement on a entangled Bell pair, at that point you can't see, how can I put this? At that point, you maybe don't know which of the two was left and which of the two was right. But knowing that if you measure one of them as being left, you do know that the other one is right. So I'm sorry if that makes no sense. In other words, when you measure the collapse of an entangled state, again, thinking mathematically, you're projecting 4 dimensions down to 2. If you've constructed this 4-dimensional state to be very special, then that projection down still does tell you something. Because you're, so to speak, projecting down at the right angle to see more than if you project down at a different angle. But I'm sorry if I'm not clear because I don't really understand this myself, how projection down from a higher dimensional product space is equivalent to measurement. I'm still actually learning more physics. But thank you for your patience in answering my questions.
I think, well, it's more of a conversation, right? We are all exchanging ideas. Nobody, no one, I mean, no one here is an expert. It's an evolving field. We're all bouncing off ideas by asking these questions and, you know, getting each other's view. We can perhaps learn from each other. That's my whole purpose to coming to these places. You know, I love it.
That's a great thing, yeah.
I think, I'm sorry to say, I felt that the person who was presenting today was a bit defensive and it was very difficult. So that's why I kind of shut up. But I like this, you know, this kind of conversation because it makes, we are here to learn, you know, and it's bouncing off ideas.
Yeah, no, I understood that she is just starting out and she's written, you know, a paper, and that some of these questions are beyond the scope of her paper, but I thought she was very clear in explaining within context.
Exactly, yeah.
Exactly, I agree.
Yeah, and yes, she had to be defensive. And my question to you, George, is where did you read that mathematics about that projection?
This is based on my reading of Bell's classical paper where he proves his inequality.
Bell's inequality, but you know, maybe it adds confusion that this was violated already.
Right, but
okay, so that adds confusion to all the mathematical structure of this thing called projection and trying to translate it to the quantum world.
Right.
Because these are two confusing fields that now are becoming super incoherent in quotes and no quotes.
Yes, I mean, and I admit that when I talk about measurement in the sense of physics and irreversible collapse from the wave picture to the binary picture, either this happened or that happened, I don't understand that. But this is again my understanding of the Bell paper just as mathematics, that you can show this inequality by just using tensor algebra. And I was trying to explain how you can kind of visualize this very simplified when you project something down from 3 dimensions. Of course, you lose information. A sphere turns into a circle, say, or a square, or a cube into a square. But if your object in the higher dimensions is oriented in a certain way with respect to the basis you're projecting, you can deduce more from that projection than from other projections. And I'm hypothesizing that is also what you can do experimentally, that you can manipulate the measurements to gain more information. But again, Can I
rephrase what you're saying, because I'm trying to understand what you're saying.
Sure.
And by restricting to certain angle of projection, you sort of intuitively guarantee or help the possibility of reconstruction.
Yes.
Whereas if you project without that restriction, you're really lost in space, if I can use that word.
Yes, and if I could make another analogy, which is also between the quantum and classical worlds, if you do, what's it called, tomography, MRI.
Yes, tomography, that's okay.
You are taking, in the classical world, you're taking, I don't know, hundreds of thousands, millions of measurements, and then you are doing a reconstruction from that of a three-dimensional situation.
Right. But there you take advantage of cancellation of all the misleading parts of just one or two projections.
Yes, but
okay, because yeah.
Yeah, again, I am very weak.
It's
on
a lovely example, actually.
Thank you. I will admit that I am weak on the physics. My background is more in pure math and computer science. So I'm just trying to make these analogies, and my apologies to anyone here that understands this better.
No, I think
my weakness is in mathematics side sometimes, because I like to visualize everything. If I can't see a picture of something, I'm a visual person, and in my mind, everything has to make a sense in terms of three-dimensional space, or or colors, or this and that. And if it doesn't, I don't really. And mathematics is good as long as it makes that science, that kind of connection, because vector, I can really visualize it in space, and I really understand vector is a speed and a magnitude in one sense, or it has, or in relation to a scalar. But a vector in data science means completely different thing, but mathematically same thing. And similarly, a tensor is so I like physics for that nature. I think it's beautiful.
And
no doubt, absolutely.
I think the block sphere is a beautiful visualization.
Yes.
But it's kind of limited to, one complex dimension, which is one qubit, which reduces physically to a two-dimensional real sphere that we can picture. It is very much harder to visualize the product of two qubits. Again, I mean, here a qubit is a mathematical object.
Not quite, because so yes and no. I mean, that is a mathematical representation, and block sphere pretty much allows you to view it in a three-dimensional space. Yeah. But if you look at the mathematical product of those two, it is actually the same as any scalar product. Sorry, not the word scalars, as a classical product, except that it is for a qubit.
Yes, but the only reason that works is that the complex numbers are a division ring over the reals. So I don't understand how, when you have many qubits in n complex dimensions, you have 2n real dimensions, and you go higher in complex and real dimensions, you lose the nice algebraic properties of being a division ring like the complexes. You can go up one more dimension to 3. Again, I'm talking real, and you get actually, no, you can go up to 4, and you get the quaternions and so on. But eventually you no longer even have an algebra. You can only add and multiply and scale and multiply. You can't divide. I'm sorry if I'm not clear there. So I don't quite understand what the visualization is of more than 2 qubits. So not even mathematically. So I'm still trying to learn this stuff myself, both the math and even more so the physics.
Sorry, I got a bit lost there. I have found the paper that I was mentioning earlier, and the title of the paper is in the Journal of Physics from Austrian University, published on the 16th of September 2021, written by Miguel Gallego and Boriwoke Dakovic. And the title of the paper,
Miguel Delego?
Miguel Gallego, yes.
Gallego.
Yes,
Gee.
and the title of the paper is Macroscopically Non-Local Quantum Correlations.
Oh, thank you very much. That might narrow down my Google search.
Non-local?
So macroscopically non-local quantum correlations.
Quantum correlations. So it's not the, yeah, okay.
Type too slow. Macroscope.
Well, I expect this to be a mathematical paper, not physics.
It is a mix of both, actually. I mean, it comes in the quantum domain, related to quantum physics mostly, but it has huge implications for quantum computing itself, as well as our view of our basic science, which underpins quantum computing. And I think this is one of the, and this is from University of Vienna. There's some beautiful, really, really good research papers coming out for a very long time from Vienna. So
Right.
I think this has to be a cutting edge. But again, it's very basic paper. If you go through it, it's very basic, but the implications are quite profound.
Okay, and now it is on the chart, right?
Okay, that's.
03988. Okay.
Oh, thank you. Okay, yes, I see it on the archive.
Yeah, that helps with the Googling. Instead of putting words, you just put these 8 numbers or 9 numbers and you get them.
Thank you so much. This looks like something I can at least tackle and at least see the limits of my understanding and read other things.
Yeah, we'll be very
You know,
glad to discuss it, George, because
George,
we come
why
from
don't
different angles.
George, I mean, Washington Computer Society, which we are currently part of, they're always looking for, Helen, if that's okay, I continue this. They're always looking for people to do some, present some material and all. How about you work out something, mathematical and present over here, take the users from, from very basic to building up the background all the way, from, number system to tensors and all of that. That would be quite nice. And I'll be quite
Great
interested.
idea.
Helen, would that be okay?
So you mean we should organize a workshop?
No. I mean,
the more advanced.
Yeah, I mean, a paper that George can present with his mathematical background that would cover all the quantum bits from a mathematical standpoint.
Yeah, sure. Yeah, George can be the next speaker if he wants.
That I don't know about being next. That might take me a few months to put something together, because it would mean that I would have to truly understand it myself. As Feynman said, if you can't explain it to a freshman, you don't understand it. And that is as true of math as of physics. But in a few months, I could maybe put something together on a small subset of the math, like maybe from numbers to complex numbers to quaternions to vectors and tensors, but only on a very introductory level.
Yes, that would be great, actually, George. We appreciate that, and Helen is the one who's scheduling, and I'm sure that she can, fix some dates in future, 2-3 months.
Yes, because right now I am studying. So
How about in December, George?
yes, if I that would maybe give me time to put something together, even a sketch of a paper and a slide deck to try and present some of this. The problem is that much of this math is not in undergraduate type of books. It's scattered in more advanced places. And so and even when I talk to physicists, they know, you know, I sometimes have to explain what to me seems simple math concepts that were not part of the way they learnt things as a physicist. Not that I'm claiming any great expertise. I'm a beginner in math too after 40 years. But what I like about this community is people's willingness to converse and learn from each other, so that if, like I said, if I can put something together that presents, you know, number systems, vectors and tensors into a short presentation, that would help me understand. And if it's helpful to somebody else, that would be wonderful too.
Yeah, anything you can squeeze into it, you know, 3 months time or 1 month time or 2 months, we'll be looking forward to it.
Yeah. Okay, well, thank you for your invitation, and thank you for your patience with me.
No, we thank you. We look forward to it. Okay. So if that's it, then we can close it. It's already past 3. Helen, you can close it.
So please join our next week event, Quantum Interference of Light with Dr. Galvez. Thank you.
Thank you so much, everyone. Bye-bye.
Yeah, thank you.
Thank you all.